All right, so welcome back. This is second part for the section two, and what I hope to do is again just create these particular simulation for this particular figure here. We're gonna change the structure from this one that has two layers into this one. And I've already created these code system here. Just copy pasted all the code from the first part of the section to this part and make an example. We can run it and it's still showing the previous result. So what we need to do is to make some changes and to really demonstrate to you why we create this object-oriented programming and how that really helps you to change the code and allows it to simulate the things that you're curious about without really getting into the source code. And that's the beauty of it. Um, and I myself actually have not worked it out, so we'll see. I think it's going to be straightforward. So the first part, this part is just creating those assembly and the classes and the objects. I think we don't need to change it. We can just keep everything the same. And then the nodal coordinate, we do need to change it. So this system we're looking at here, 1, 2, 3, 4, 5, 6. It has 6 node. And I definitely don't need a 2.5L. That's the original top. 1.5L, also too high. 2L in the Z directions are here. So those are for the previous structures. I don't think I need those. So these are gone. And 1, 2, 3, 4, 5. Okay, this one is at the middle. So I only need to add the 6th node here. And for this one, that one is 2L in its height. All right. So let's try to see if that's exactly what we've been doing. Oops. I should stop it at here. And let's run it. There we are. So we do end up have a node coordinate that's exactly what we're hoping to get for this particular design here. So the next thing is to change how these bar elements are connected, right? So we still have 1, 2, 2, 5, 1, 5, 3, 4. That one we needed. 3, 5, 4, 5. Those I do needed. And then there's no node 8, so I need to change everything from here. So I need a 3, 6 according to that figure up there. And then I need a 4, 6. So it seems that this is all of the system I need. So that counts the number of bars for the normal bars. 1, 2, 3, 4, 5, 6, 7. Oh, there's actually 1, 2. Okay. I think in our example, we actually don't have 1, 2 there. All right, so that's deleted. And that should work. That should give us the result we're looking for. And then for the active bars, we only have 1, 3, and 2, 4. That's the node, right? So the first bar, the first active bar connect node 1, node 3. The second one connect node 2, node 4. Okay, that will work. And we can keep these properties just using the properties we've been using and don't bother with it at this moment. Initialize the bar and okay, this is the second breakpoint that we hope to stop, and let's see. Let's try to see if we can get the plot right. Oh, it's not working. The index does not match. Oh, there we are. So for the properties, the A vector, E vector, the Young's modulus vectors, we have not changed their dimension yet, so let's change it. For the active bars, we only have two, so it's no longer a 4x1 vector. So that's not matching, so that's causing the problem. And for the bars, normal bars, we have 1, 2, 3, 4, 5, 6, 7. So instead of have 13 normal bars, I only have 7 now, and these should get rid of that arrow. Okay, great. That's good. Um, so this is exactly these structures that we are hoping to get, right? And after that, although we have not talked too much about the loading, but I don't think it's too hard to read, right? So I guess the only thing we need to change here is the actuation or the extension of the target extension and contraction in the bars, and also the support, because that's all that we've been changing. And right now we have just 6 node, and so basically 7, 8, 9 are from the previous example, and we no longer need them. And we still fix node 1, node 2 in all the, so they're fixed in space. So X, Y, Z direction, they're all fixed. And because we want to make these a planar problem, so for node 3, 4, 5, 6, the Y direction is fixed, but it's allowed to be moving in XZ plane. So we assume that this is an XZ plane. So this is node 1, node 2, it's fixed in space, 1, 2. That's why it's all ones, whereas the rest are 0, 1, 0. So that will work. And for the target length of the active bars, we only have 2 of them. So there's no index 3 here, and there's also no index 4 here. So basically, we just get rid of that, and I believe that will work in our example. Yep, so this should directly give us that result we are looking for. Look at that. So it just takes us, I don't know, less than 5 or 7 minutes to change a code to reproduce what we're looking for here. So that's the beauty of using object-oriented programming. So just imagine that if you write everything in a for loop in a single file for something like these, in order to change it, to just make minor changes to your structures, you probably need to really make a lot of changes throughout the code and fix a lot of dimension mismatch here and there to get things work. But if you package your system using object-oriented programming, using classes, using nicely organized functions, your life is so much easier. And that's really one of the reasons why we hope to organize these set of live code and also live textbook and the code package using object-oriented programming. All right, so hope this is a convincing message to you. And coming back next time, we will still be working on 2 more examples before we move on to tell you the theories behind the derivation of these bar elements and also the nonlinear Newton-Raphson solver, which we already are using it to capture the deformation of these active truss. So, all right, with that, thank you for your attention and have a great day.